we have talked about the gravitational force near the surface of the Earth, F equals mg, where g is 9.81 meters per second squared. But now we're going to talk about what is sometimes referred to as universal gravitation, which really just means the more general description of gravitation, or you could be more ambitious and say that means the gravity that holds the universe together. I'm not sure what they mean when they say universal. What it basically says is that all objects attract each other due to gravity. And you may say, all? Really, all? All? The answer is yes. Yes, all. Everything in the universe, even this little proton in my thumb and something in the Crab Nebula somewhere, yes. Very small force, but they all attract each other. Even here we have Hal and we have one of the plastics. I've got them a meter apart and they do feel an attractive force due to gravity. So let's calculate it. When you're calculating force between two objects in this case, here is one, here's the other. You want to draw an axis between them, because you can always draw a straight line axis when you just have two objects. And the distance you consider is between the center of each object. If it's a nice sphere or a spherical shell, if it's uniform mass, then you worry about its center. It acts like all the mass is at the center. So we'll call this r, the distance between them, and we'll call this one m1 and this one m2. Masses don't have to be the same for what we're doing here. So the force you're going to get between them is, we know force is a vector, but at first we want to calculate just the scalar. We want to calculate just the magnitude. And it's equal to a new constant, big G, mass of the first times the mass of the second over the second separation squared. So we always say big G because we want to distinguish it from little g. Little g is 9.81 meters per second squared, acceleration near the surface of the Earth. Big G is a universal constant. Okay, it does not just apply to the surface of the Earth. It applies everywhere, and it's much harder to remember. 6.674 times 10 to the minus 11. And if you ever forget the unit, you can just look at this formula and remember it. It must come out in newtons. It must be newtons, and it must have meters squared in the top to cancel that, and it must have kilograms squared in the bottom. Newton meters squared per kilogram squared. Must be correct. So that's big G. That's the constant you need to calculate gravitational forces. If we wanted to think about then the force in this case, we have Hal here. In the case that we have here, we got 1.8 kilograms here, and we've got 0.13 kilograms here, and I have them apart by 1 meter. Then the force they feel a gravitational force. They're not rolling towards each other because it's only 15.6 piconewtons. Oops, 15.6 pn, piconewtons, so that's 10 to the minus 12 newtons. So that's really small, so not quite enough to overcome the static friction to make them move towards each other. But even everyday objects feel a gravitational force between each other. The direction is always attractive. All right, so in this case, Hal feels its force this way, and the plastic feels its force that way. And the magnitudes are the same. That's another key. You might think that, oh, maybe the heavier one puts a bigger gravitational field on the lighter one, so the lighter one feels more. No, same, right? It's the same expression. This is the magnitude of the force, and the same force is applied each way, which has to be true by Newton's third law. Right? For every action, there's an equal and opposite reaction. Also, it has to be true to conserve momentum. If we had these things out in space and they felt different forces for the same amount of time, we would create a net momentum, and we have to conserve momentum. So all these things are true. the direction's attractive, and the magnitudes have to be the same. So let's see what all we can do with this simple force law.